In this video, we will learn how to describe polar and nonpolar solvents. We'll examine how intermolecular forces between molecules affect solubility and determine the meaning behind the phrase like dissolves like. Before we can examine how polar and nonpolar solvents interact, let's first review some key concepts. Electronegativity is the tendency of an atom to attract the shared electrons of a bond. Looking at the periodic table, electronegativity generally increases as you move up a group and from left to right across a period. The Pauling electronegativity scale, a unitless scale which ranges from 0 to 4, gives us a way to quantify the electronegativity of atoms. Fluorine has the highest electronegativity value of 3.98, while elements like potassium have much smaller electronegativity values. The difference in the electronegativity values of bonded atoms can be used to determine whether the bond tends to have ionic, polar, or nonpolar characteristics. When the electronegativity difference between two bonded atoms is less than 0.4, the bond tends to be nonpolar. When the electronegativity difference between two bonded atoms is greater than 1.8, the bond tends to be ionic. And when the electronegativity difference between two bonded atoms is between 0.4 and 1.8, the bond tends to be polar. In an ionic bond, the electronegativity difference is so great that the more electronegative atom has become a negatively charged ion, and the less electronegative atom has become a positively charged ion. Sodium chloride is an example of a compound that exhibits ionic bonding. In a polar bond, the electrons of the bond are unequally shared and are drawn towards the more electronegative atom. This results in the more electronegative atom having a partial negative charge, represented by the symbol delta minus, while the less electronegative atom gains a partial positive charge, represented by the symbol delta plus. A dipole arrow can also be used to represent the partial negative and partial positive sides of the bond. Hydrochloric acid is an example of a compound that contains a polar bond. In a nonpolar bond, the electrons of the bond are equally shared between the two atoms, so neither atom has a partial positive or partial negative charge. A molecule of chlorine contains a nonpolar bond. When a molecule contains only two atoms, like the examples shown here, it is fairly easy to determine if the molecule tends to be polar or nonpolar using electronegativity differences. But when the molecule contains more than two atoms, this can become quite difficult to determine. A polar molecule contains polar bonds and will have a non-uniform electron density. This means that some regions in the molecule will have a partial negative charge, while other regions in the molecule have a partial positive charge. Some examples of polar molecules include water and methanol, commonly called formaldehyde. Nonpolar molecules may contain polar or nonpolar bonds, but they must have a uniform electron density. In general, if all of the atoms in the molecule are the same, the molecule only contains carbon and hydrogen atoms, or the polar bonds are symmetrically distributed, the molecule will be nonpolar. Now that we can recognize polar and nonpolar molecules, let's examine the solubility of these substances in one another. Solubility is the tendency of one substance to dissolve in a solvent to form a solution. Let's consider two containers of water. To the first container, we'll add some vegetable oil, and to the second container, we'll add some isopropyl alcohol, commonly called rubbing alcohol. Water and oil do not mix to form a solution. We can describe water and oil as immiscible, incapable of being mixed to form a solution. Rubbing alcohol and water do mix to form a solution. we can describe water and rubbing alcohol as miscible, capable of being mixed to form a solution. But why do oil and rubbing alcohol behave differently when mixed with water? To understand what is occurring, we need to take a brief look at intermolecular forces. Intermolecular forces are electrostatic forces that exist between molecules. As we stated earlier in the video, nonpolar molecules, like a molecule of bromine, do not have regions of partial charge. Even so, two nonpolar molecules will exhibit a weak electrostatic attraction towards one another. This electrostatic attraction, called dispersion force, is due to the random motion of electrons in the molecule and will be covered in more detail in another video. Polar molecules do have regions of partial positive and partial negative charge. When two polar molecules are near one another, there exists an electrostatic attraction between the partial positive charge of one molecule and the partial negative charge of another molecule. An even stronger intermolecular force exists between certain polar molecules that contain a hydrogen atom bonded to an oxygen, nitrogen, or fluorine atom. There is a very large electronegativity difference between a hydrogen atom and an oxygen, nitrogen, or fluorine atom. The large electronegativity difference results in larger partial negative and partial positive charged regions in the molecule. The hydrogen atom of one molecule, which has a large partial positive charge, experiences a strong electrostatic attraction to the lone pair electrons of an oxygen, nitrogen, or fluorine atom of another molecule. This very strong electrostatic attraction is called hydrogen bonding and exists between a hydrogen bond donor, a molecule with a hydrogen atom bonded to an oxygen, nitrogen, or fluorine atom, and a hydrogen bond acceptor, a molecule that contains an oxygen, nitrogen, or fluorine atom with lone pair electrons. With this understanding of intermolecular forces, let's return to the example of oil and rubbing alcohol mixing with water. We just learned that water molecules are polar and exhibit hydrogen bonding with other water molecules. Vegetable oil consists of triglycerides, which we will abbreviate as TG. Triglycerides are compounds that contain 3 ester groups with large hydrocarbon chains and are nonpolar. This means that triglycerides exhibit weak electrostatic forces with one another. A molecule of triglyceride and a molecule of water do exhibit electrostatic attractions with one another. This electrostatic attraction is stronger than the attraction between two triglyceride molecules, but is weaker than the attraction between two water molecules. As water molecules are more strongly attracted to one another than to the triglycerides, the two substances do not mix. Like water, the isopropyl alcohol molecules of rubbing alcohol are polar and can form hydrogen bonds with other isopropyl alcohol molecules. Water and isopropyl alcohol molecules can form hydrogen bonds with one another as well. This intermolecular attraction is similar to the attraction each substance had on its own, and the two liquids mix together. In general, solutes and solvents that exhibit similar intermolecular forces of similar strength are likely to dissolve in one another. We often express this generalization with the phrase like dissolves like, meaning that nonpolar solutes tend to dissolve in nonpolar solvents, and polar solutes tend to dissolve in polar solvents. Ionic solutes also tend to dissolve in polar solvents. A sample of sodium chloride contains positively charged sodium cations and negatively charged chloride anions that are electrostatically attracted. When added to water, the negatively charged chloride anions interact with the partial positively charged regions of the water molecules, and the positively charged sodium cations interact with the partial negatively charged regions of the water molecules. The ions dissociate from one another and become surrounded by water molecules, thus forming a solution. It's important to note that not all ionic solutes dissolve in polar solvents. Ionic solutes only tend to be soluble in polar solvents when new, stronger electrostatic interactions are formed. Now that we have examined the solubility of substances in polar and nonpolar solvents, let's make a list of some common solvents that we can choose from. Some common nonpolar solvents include hexane, benzene, and carbon tetrachloride. Polar solvents can further be classified as either protic or aprotic. Protic solvent molecules contain a hydrogen atom bonded to either an oxygen, nitrogen, or fluorine atom, and exhibit hydrogen bonding. The prefix "prot" in protic indicates that these molecules are proton or hydrogen ion donors. Examples of protic solvents include water, ethanol, and methanoic acid, commonly called formic acid. The A in aprotic means not. So aprotic solvents do not contain a hydrogen atom bonded to an oxygen, nitrogen, or fluorine atom, do not exhibit hydrogen bonding with other aprotic solvent molecules, and are not proton donors. Examples of aprotic solvents include dichloromethane, propanone, commonly called acetone, and tetrahydrofuran. It's often useful to think of nonpolar and polar solvents as a continuum. Some solvents can be considered extremely polar or nonpolar, but most solvents fall somewhere in between. Some compounds may even exhibit both polar and nonpolar characteristics at the same time. Let's consider, for example, ethanol and pentanol, two alcohols. While both molecules have a similar structure, ethanol is miscible with water, but pentanol is not. We can see that both molecules contain an oxygen atom bonded to a hydrogen atom, a group that is polar and can form hydrogen bonds. We also see that both molecules contain a hydrocarbon portion that is nonpolar. As pentanol is immiscible with water, the large nonpolar hydrocarbon chain must affect its solubility more than the polar OH group. In general, we find that for small alcohols and carboxylic acids, the polar portion of the molecule contributes to the overall characteristics of the solute more than the nonpolar portion. As such, these molecules tend to dissolve in water. But as the length of the carbon chain grows, the molecule tends to exhibit more nonpolar characteristics. Thus, large alcohols and carboxylic acids tend to be immiscible with water. Now that we've examined the solubility of substances in polar and nonpolar solvents, let's take a look at a question. Which of the following statements describes bromine dissolving in hexane? A nonpolar substance dissolving in a polar solvent. B, a polar substance dissolving in a nonpolar solvent. C, a polar substance dissolving in a polar solvent. D, a nonpolar substance dissolving in a nonpolar solvent. First, let's define the terms polar and nonpolar. A polar molecule will have a non-uniform electron density. This means that some portions of the molecule will have a partial negative charge, and some portions of the molecule will have a partial positive charge. Nonpolar molecules will have a uniform electron density. This is the case when the electrons are equally shared in all of the bonds in the molecule, or when the polar bonds in the molecule are symmetrically distributed. Bromine is a diatomic molecule consisting of two single-bonded bromine atoms. As the atoms are the same, they will have the same electronegativity. This means that the electrons in the bond will be equally shared between the two bromine atoms. Thus, the molecule of bromine is nonpolar. As bromine is the substance being dissolved, we can eliminate answer choices B and C. Hexane chemical formula C6H14 only contains carbon and hydrogen atoms. The electronegativity of a carbon atom is approximately equal to the electronegativity of a hydrogen atom. Because the electronegativity values are so similar, we can consider the electrons in a carbon-hydrogen bond to be equally shared. As a molecule of hexane only contains nonpolar carbon-carbon and carbon-hydrogen bonds, hexane will be nonpolar. Therefore, the statement that describes bromine dissolving in hexane is answer choice D, a nonpolar substance dissolving in a nonpolar solvent. Now let's sum up this video with the key points. Nonpolar solvents have a uniform electron density, while polar solvents do not. The non-uniform electron density of a polar solvent results in the molecule having regions of partial positive and negative charge. The phrase like dissolves like can be used as a generalization to recognize which solutes tend to dissolve in which solvents. In general, polar solutes tend to dissolve in polar solvents, and nonpolar solutes tend to dissolve in nonpolar solvents. Substances, particularly liquids, that mix to form a solution are miscible. Substances that do not mix to form a solution are immiscible. Solvents may be classified as nonpolar, polar protic, or polar aprotic. Polar protic solvents can form hydrogen bonds, while polar aprotic solvents cannot. This is because polar protic solvents contain a hydrogen atom bonded to an oxygen, nitrogen, or fluorine atom.